Okay, as promised, this video is on equations for the plane, and we're going to sneak something else in also. All right, share screen. Let's go to our notes. A little bit off, but here we go. Equations for the plane. Okay, suppose, just suppose we know one point on a plane. Let's call it P. X naught, Y naught, Z naught, as shown here, and we have a vector that's orthogonal to the plane. We'll call it N. Let's say its coordinates are ABC, or its components. This vector is called the normal vector. The set of all points Q, let's just say X, Y, Z, such that the vector PQ is orthogonal to N. That set forms a plane, and so this gives us the vector equation of a plane, specifically the dot product of n with the vector PQ is equal to 0. Recall that this is true because two vectors are orthogonal if and only if their dot product is 0. Okay, so rewriting this equation, we're going to find another equation to represent a plane, a scalar equation. So we're going to plug in the PQ, which is x minus x naught, y minus y naught, z minus z naught as its coordinates. And we get this equation that's already on the page. And when we actually compute the dot product, we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. And that is the scalar equation of the plane. Right. Now let's do an example. We want to determine if the plane given by negative x plus 2z is equal to 10, and the line given by x equals 5, y equals 2 minus t, z equals 10 plus 4t, or orthogonal, parallel, or neither. Okay, so the nice thing is that, well, we can determine the normal to the plane. And we can get that directly from the scalar equation. So that's going to be given by the first coordinate is the coefficient of x, which is -1. The second coordinate is the coefficient of y, which is 0. And the third coordinate is the coefficient of z, which is 2. Similarly, a vector v parallel to the line is, again, as we did in the last video, we'll use the direction vector. And that direction vector, recall the components are the coefficients of t in our parametric equations. So for the x component, we have nothing, so 0. For y, the coefficient is -1. And finally, we have a 4. So those are our two vectors. Now, here's the idea. If these two vectors are parallel, so if n and v are parallel, well, then that means that v is orthogonal to the plane, but it's also parallel to the line. And so since it's parallel to the line, right, since that's all, we already knew that, since v is also parallel to the line, so it's orthogonal to the plane, it's parallel to the line, sorry, it's orthogonal to the normal vector and parallel to the line, well then v is orthogonal to the plane and parallel to the line, and so that tells us that the line and the plane are actually orthogonal. And so how do we know if the vector is parallel to the line? Well, if the vector is parallel to the line, then the cross product, if the normal vector, sorry, be more specific, the normal vector is parallel to the line. Wow. Yeah, that's right. If the normal vector is parallel to the line, then the cross product of the normal vector with v is going to be 0. Because if you'll recall, the magnitude of the cross product is the magnitude of the two vectors, the product of that times sine of theta. Parallel means that theta is either 0 or 180 degrees or pi in radians, which means that the sine of it would be 0. And so, in other words, right, n cross v is going to be the 0 vector. Okay, so let's check it out. What is the cross product of n with v? All right, so put our unit vectors as the first row. N is our second row, so that's -1, 0, 2. And the components of v give us our third row, 0, -1, 4. So we're going to get the determinant of the matrix 0, 2, -1, 4 times I minus the determinant of the matrix -1, 2, 0, 4 times J plus the determinant of the matrix -1, 0, 0, -1 times K. We can easily see that that determinant is going to give me, let's see, going to get 2I minus a -4, so that's plus 4J, and plus K. Under no circumstances is this the 0 vector. So that tells me that the vectors n and v are not parallel. Well, that's good, because that means, well, I don't know if it's good. It's good in terms of if we are interested in seeing if the line is orthogonal to the plane. So we have, no, it's not orthogonal to the plane. Okay, if the line is parallel to the plane, well, if the line's parallel to the plane, then that means that n and v are orthogonal, which means, of course, that the dot product is 0. So let's check the dot product. The dot product is going to give me, what, 0 times -1 plus -1 times 0 plus 2 times 4, or 4 times 2, n times v. Oops. Well, order doesn't count when you're doing this. Remember, n times v is equal to v times n, but just for the sake of putting things in the order that I had it, right, the point is this is equal to 8, which is not 0. So the vectors are not orthogonal. So we've shown that the line and plane are not orthogonal. And so this shows us that n and v are not orthogonal, which means the line and the plane are not parallel. Which leaves us, of course, the third case. So to conclude, the line and the plane are neither orthogonal nor parallel. And now let's talk about what happens when two planes exist together, i.e., parallel and intersecting planes. So how do we tell if two planes are parallel? Well, if two planes are parallel, then their normals are also going to be parallel. There you go. What if not? Well, if not, then the planes are going to intersect. And if they intersect, they're going to intersect in a line. And how do we determine the line of intersection? We just solve the system of equations defined by the planes. Instead of going blah, blah, and writing a bunch of equations, I think it's best in this instance to do this by example. So I will do that. Let's determine if the planes below are parallel, orthogonal, or neither. If not parallel, let's determine the line of intersection. So first of all, let's find the normals. So the normal for the plane 3x plus 6y minus 5z equals -3. Henceforth, the first plane is, we'll call that n sub 1. That's going to be 3, the vector 3, 6, -5. And the normal for the second plane is going to be, we'll call that n sub vector n sub 2, is the vector -2, 7, -1. Okay, first of all, we see that n1 is not a scalar multiple of n2. Why do we know that? And it's not because I wrote the example down ahead of time and I have the answer, by the way. So the reason is, if you look at the vectors, the first components have different signs, but the other components are of the same sign. Right, the first component of n1 is 3 and of n2 is -2. So but because the other components have the same sign, we know it's not scalar multiples. Okay, so that tells me that n1 and n2 are not parallel, which tells me that the what do you call them? The planes are not parallel. Awesome. Okay, by the way, if we take the dot product of those two vectors, we get 3 times -2 plus 6 times 7 plus -5 times -1, which is 34, which is not 0. We also know that n1 and n2 are not orthogonal, which tells me the planes are not orthogonal. You know, just as extra information. So let's get the line of intersection. So we literally take the two equations of the planes and try to eliminate one of the variables. Let's just eliminate x. So to eliminate x, I'm going to multiply the first equation by 2 and the second equation by 3, and then I'm going to add them together. But when I multiply by 2, I get 6x plus 12y minus 10z equals -6. And the second one gives me -6x plus 21y minus 3z equals 21. And so, as I said, the next thing I'm going to do is I'm going to add those two together. So we're going to do a plus. And when I add them together, what do I get? Well, I get 33y minus 13z equals -15. Now we're going to solve for y as a function of z. And if I do that, I'm going to get y is equal to apparently when I multiply, hold on, let me go back up here. 3 times 24 is 72. 72 minus 6 is 66. There, that's much better. Sorry about that error. Good thing I caught it. So y is going to be 66 plus 13z over 33, which is 2 plus 13 over 33 times z. All right, so let's get our parametric equations of the line. So here's how we're going to do it. Let's write z equals, well, let's write z as a function of t. Okay, let's write z as a function of t of a parameter t. So the easiest thing for us would be let z equal 33t, because if I do that, then I get that y is going to be 2 plus 13t. Last but not least, substitute into either the first or second equation plane of the plane, the original equation. So the first or second equation to find x. Okay, I will use the first equation. So I have 3x plus 6 times 2 plus 13t minus 5 times 33t is equal to -3. Without showing all the work, I'm just going to go with x is equal to -5 plus 29t. So line of intersection has the parametric equations, and we could find any other form we wanted. But let's do the parametric equations because we already got them. So x equals -5 plus 29t. Y equals 2 plus 13t, and z equals 33t. And that's it. Now, if I wanted to do a little more and find the angle between intersecting planes, well, that angle is just going to equal the angle between the normal vectors. And then we can find the direction cosine using dot products. And since this is stuff we've already talked about, I'm actually going to, and the textbook has some really good examples, I'm going to refer you to the textbook for that. Now, I'm just going to pop in a short, no, you know what? I'll make that a separate recording. All right, so we have suggested exercises, and you can see next time we're going to quickly discuss quadric surfaces. Okay, so that is that. I will